Okay, we're going to talk about molecules and compounds. So let's talk about an element versus a compound. So sodium is a shiny, reactive, and poisonous metal. Chlorine is a pale yellow gas, which is equally reactive and poisonous. But when we combine these into a compound, we form sodium chloride or table salt, which is relatively harmless and it's flavorful. So when elements combine to form compounds, their properties completely change. Compounds display constant composition. So we have the law of constant composition, which says that all samples of a given compound have the same proportions of their constituent elements. So let's do an example. So we have two samples of carbon dioxide. They both come from different sources, and we decompose them into their constituent elements. So one sample produces 4.8 grams of oxygen and 1.8 grams of carbon. The other sample produces 17.1 grams of oxygen and 6.4 grams of carbon. So if you look at the ratio of oxygen to carbon, the mass of oxygen to mass of carbon in sample 1, we get a ratio of 2.7. If you do it for sample 2, we also get a ratio of 2.7, which we should get. Because again, no matter where the compound comes from, if it's the same compound, their ratios of elements that form that compound should be exactly the same. Okay, let's talk about how we write chemical formulas. So chemical formulas are how we represent compounds. We talked about element symbols. That's how we represent elements. Well, compounds take elemental symbols and they put them together. So they indicate the elements present and the relative number of atoms. We normally list the metal-like element first when we write a chemical formula. So for example, H2O shows us that we have a 2-to-1 ratio of hydrogen to oxygen for water. So we write the symbol for hydrogen is H. The subscript 2 indicates that we have 2 hydrogen atoms. Then we have the symbol for oxygen, O, and we have an implied subscript of 1 indicating 1 oxygen atom. So if we have just 1 atom in the ratio, we don't put the 1 there. It's implied. Here's carbon monoxide and carbon dioxide. So carbon monoxide, CO, we have 1 carbon and 1 oxygen. CO2 means we have 1 carbon, we have 2 oxygens. The subscript 2 means we have 2 oxygens for every 1 carbon. Let's talk a little bit about polyatomic ions, and we'll talk more about these in nomenclature. But a polyatomic ion is just a group of atoms that act as a unit, and they have a charge associated with them. So an example of a polyatomic ion is the nitrate ion, NO3-, and it acts as an ionic group. So when we write a chemical formula with polyatomic ions, this is how we do it. Okay, so if we have magnesium nitrate, we have the symbol for magnesium, Mg. We have an implied subscript indicating 1 magnesium atom. Then the symbol for nitrate, again, is NO3. We put brackets around that to show that it acts as a group. This subscript after the brackets of the NO3 means that we have 2 NO3 groups. Within the brackets, within the NO3, we have the implied subscript saying we have 1 nitrogen atom per NO3- group, and this 3 after the oxygen means we have 3 atoms per NO3 group. Okay, there's a couple different types of chemical formulas, and we'll talk more about these later. But for now, you should just know an empirical formula is the simplest whole number ratio of atoms for each element in a compound. And a molecular formula is the actual number of atoms of each element in a molecule of the compound. So for example, hydrogen peroxide. The molecular formula for hydrogen peroxide is H2O2. So in that one molecule of that compound has 2 hydrogens and 2 oxygens, but its empirical formula is HO because it's the simplest whole number ratio of atoms of each element of compound. Okay, let's look at this. So as we talked about before, we have pure substances. That can be broken into elements or compounds. So look at the element side. Elements can either be atomic or molecular. So for example, an example of an atomic element is neon, Ne. So there's just 1 neon atom. Molecular elements, for example, O2, will always have 2 oxygen atoms bound together, but they're still elements. Then we have compounds. We have molecular compounds and ionic compounds. So molecular compound example, that is water, H2O. That means we have one molecule of water has 2 hydrogens and 1 oxygen. In an ionic compound, we have, for example, in salt, sodium chloride, we have 1 sodium chloride formula unit, but it's just a part of a lattice. And so the formula unit is just the simplest unit within an ionic compound, but it's just one part of the lattice. It just shows you the ratio, and that says within sodium chloride, we have 1 sodium for every chlorine. We'll talk about that a little bit more later. Okay, let's talk about molecular compounds. They're composed of 2 or more nonmetals. So for example, H2O, water, CO2, dry ice, C3H6O is acetone. And then ionic compounds are composed of 1 or more cations paired with 1 or more anions. Cations are metals and anions are nonmetals. And like I was saying before, a formula unit is the base unit of ionic compounds. It's the smallest electrically neutral collection of ions. They do not exist as discrete entities like molecules, but as a smaller part of a 3D array. So here's the salt again, right? Our formula unit is 1 sodium and 1 chlorine, but it's just a small part of this 3D array of sodium and chlorine ions.